All right, so how do we graph this? Well, step one, anytime you can factor something, you factor it. So let's see, this is going to factor as like x plus 2, x plus 1 over x minus 2. So I've graphed everything, we have factored, nothing cancels, right? So now we start. So now we want to talk about your vertical asymptotes or holes, right? And how we determine your vertical asymptote or holes is what makes the bottom 0. In this case, what makes the bottom 0 is x equals 2. Since nothing canceled, right, this is going to be a vertical asymptote. And since nothing cancels, we have no holes. So I got my vertical asymptote. The next thing I need to figure out is my horizontal asymptote. And horizontal asymptotes happen when it's bottom heavy or balanced. And in this one, okay, all right, okay. So in this particular one, this is top heavy. Notice I have an x squared over x. Since this is top heavy, right, there are no horizontal asymptotes. And anytime it's top heavy, that means you're going to have this thing called a slant asymptote. And this is what I ran out of time on Friday, so we're going to pick up here. So to find your slant asymptote, we have to change the way this looks. And the way that we change the way this looks is we divide. Like we're going to take, x squared plus 3x plus 2 and divide it by x minus 2. Now you can either do long division, but most students like doing synthetic division. So we put the 2 in the box, and we have 1, 3, and a 2 here. And we divide, and so let's bring the 1 down. 2 times 1 is 2. That's going to give me a 5. 10, that gives me a 12. And so with this synthetic division, we found out that, so this is x plus 5 plus 12 over x minus 2. And here's what this means. This means that x squared plus 3x plus 2 over x minus 2 equals x plus 5 plus 12 over x minus 2. What I just did is I changed the way this rational function looks. I made it, instead of it looking like this, when I did the division problem, I get this. These two are the exact same problem, but when it looks like this, then I can find my slant asymptote. And a slant asymptote is in behavior. And what in behavior asks is, well, what happens when x gets really big? Well, what happens when x gets really big, or basically what goes away when x is really big? When x is really big, x is really big. When x is really big, 5 is 5. When x is really big, this thing goes away, and so we don't worry about it. And so what I just found out was my slant asymptote is y is equal to x plus 5. Okay. Now, if you ask somebody else, how do you find slant asymptotes, or you look in most textbooks, or you look online, what they're going to tell you to do. How do you find a slant asymptote? They're going to tell you, divide, do the division. You can either do long division or synthetic, and they're going to say, well, don't worry about the remainder. Right? That's pretty much what every textbook I've taught out teach it. That's the way they teach it. They say, do the division and don't worry about the remainder. You're going to get x plus 5. Right? And they're absolutely right. That will give you the right answer. The reason I'm telling you that we do the long division and then we talk about how this doesn't matter is I want you to understand why the remainder doesn't matter. The reason the remainder doesn't matter is it's going to be something over an x, and x gets huge, this goes away. So if you understand that, great. If you don't understand that, you can still get the right answer. You just have to remember, okay, do the synthetic division, ignore the remainder, and this ends up being your slant asymptote. So, back in my problem, this is going to give me y is equal to x plus 5 for my slant asymptote. All right. Now, to be consistent, right, once you find your asymptotes, then you start drawing your picture. So when we draw our picture, we're going to draw our graph. I'm cheating. I'm going to have to plot a point way up here, so which is why I'm drawing down here. Here's what I know. I know that I've got a vertical asymptote at x equals 2. I've got a slant asymptote at y equals x plus 5. Well, okay, so that means go up 1, 2, 3, 4, 5. If I've got a slant asymptote, it's got a slope of 1, so up 1 over 1, up 1 over 1, up 1 over 1. So at this stage, everybody should have a picture that looks like this. Hopefully your picture looks nicer than mine, because I'm terrible at drawing. If you've got graph paper, it makes it a little bit easier. But you've got a vertical asymptote, which is the same thing we've been doing forever. And then I've got a slant asymptote, which is, whatever, this equation, that line, the equation of y equals x plus 5. At this point, we've got to plot points. We've got to figure out what's happening. And the way how you determine which points to plot, it's all about the vertical asymptote. You're always going to pick something to the left of the vertical asymptote and something to the right of the vertical asymptote. So I'm going to pick 1 and 3. And when I plug 1 into my function, I could either plug it in this version or I could plug it into the factored version. I'll just go ahead and tell you it's always easier to plug things into the factored version. When I plug 1 into the factored version, let's see, it gives me 3 plus 2 over negative 1, so I get a negative 5 for that. When I plug 3 in, let's see, 3 plus 2 is going to give me a 5, and 3 plus 1 is 4, so I get 20 over 1, and so that gives me 20. Oh, something I forgot to talk about on the last question. Actually, I did talk about it, but I never filled out in the chart because there weren't any. Let's find x-intercepts. And the way that we find x-intercepts is we set the factored version equal to 0. And the only time a fraction ever equals 0 is if the top equals 0. And what makes the top 0 is negative 2 and negative 1. So I have x-intercepts at negative 2 and negative 1. What that means in my picture is I get a dot here and here. Here's your x-axis, here's your y-axis. If you've got x-intercepts at negative 2 and 1, that means you get a dot at negative 2 and you get a dot at negative 1. And I guess I should plot the rest of this stuff. At 1, I'm at negative 5. Well, that's easy to draw. And at 3, all the way up at 20. Oh, that's going to be an issue. I'm just going to guess it's up here. All right, so everybody should have this picture drawn. Hopefully nicer than mine. Right? We got a vertical asymptote, we got a slant asymptote, we got a dot at negative 2, a dot at negative 1, we got a dot at 1, negative 5, and we got a dot at 3. Technically it's 20, but don't count up to 20. It's just way on up there and put a dot. All right, now, before we graph this picture, you need to know what slant asymptotes look like in graphs. You've got zero experience. I mean, I doubt many of you have seen a rational function with a slant asymptote. And so if you haven't seen what they're supposed to look like, it's going to be hard to draw. So what I'm going to do is, you don't need to draw any of this, just watch. Because, you get a vertical asymptote, you get a slant asymptote, There's typically 4 outcomes. And so I want you to see the 4 outcomes anytime you have a slant asymptote. So here are the outcomes. If you've got a vertical asymptote with a slant asymptote, here's a vertical one, there's your slant. your graph using the asymptotes is either going to be like a little V that hugs the asymptote here, curves around, and then curves back up. So it stays in this little part, and then over here, it's going to curve and stay in this little part. So if you have a vertical asymptote with a slant asymptote, you could have this little U-looking thing here that are in, I call them the small parts, right? Or, here's a vertical asymptote with a slant asymptote. You either get, again, you start on the horizontal, you curve up, or you curve this way. So, to be honest, anytime you have a slant asymptote, it's usually one of these two cases. These are the two most common. You either get the little U things in the small parts, or you get these wide looking things. Slightly trickier is if you've got these, you could have one part of it in the small part and one part in the big part. So it's possible when you have a slant asymptote, you could split it up this way. And actually, to be honest, those are the three cases. The fourth case is the same thing, except it's flipped down, where it kind of looks like this. But when you have a slant asymptote, you get one of these four pictures. All right? So if you've got one of these four, this is what we're looking for. So now let's go back to this picture. Everybody's got this, right? Now here's what I want everybody to do. You've got these dots in the right spot. You got your vertical and slant asymptote. What we're going to do is we're going to put our pencil on the slant asymptote. Just like when we draw with horizontal asymptotes, we put our pencil at the edge. We're going to do the same thing here. We're going to put our pencil on the edge of the slant asymptote, and we're going to draw. And we got to hit the dots. And for the left-hand side, you can almost see, looks like it's doing this. Goes up a little bit, and it comes back down, and this is seeing how we're getting in the left part. You could ask the question, well, how high does this go? You don't know. And you're not going to know until you take calculus, so don't worry about it. All I care about is that you're drawing this little curved part that goes in here. Similarly, when you go up here, put your pencil on the asymptote, it's going to curve down. As you draw this, put it on, it goes down, it's going to make a little loop somewhere and then go back up. Right? I don't know where it does the loop, right? You're not going to know that in Algebra 2. Honestly, it probably even goes down further. It might be a little lighter. I don't care. All I care about is that you know that it does a little loop so that we end up with basically this picture. All right? In the interest of time, I'm not going to fill out the rest of the chart because I want to do one more problem because it actually combines both of these ideas. And I think doing that one more problem is going to help us know how to graph. So let's stop and start.